Hello. I added to the materials one more lecture now about modeling, because I think there are some issues that were not properly covered last time. So let's take a look at the modeling a little bit further. Here is the modeling is usually done when you have some kind of real-world process that you want to model. And what are the reasons for the modeling of that process? It's usually that you want to do some sort of analytics, and there are the four forms of analytics that you can do with these systems. One is the descriptive analytics. So what you want to know that what happened in the past. You observed something from the real world process, and you want to understand what actually happened. So then you can model the process and learn that. Or you can do diagnostics, which helps to understand why that happened in the process. Or predictive analysis, to try to model what's happening next. What are the next outputs of the model? If you know the input, what is the output? This is the predictive analytics. Or prescriptive analytics, which helps you to find actions that what you need to do to get certain outputs. And because those real-world processes are, if they are unknown, you don't know these things, but you can make a kind of digital twin, a machine learning model of it, and then you can access this kind of analytics. And here is a very simple example. Let's assume that we have this kind of four-port system. It has input on the left-hand side, and it has outputs on the right-hand side. And it has also some parameters. And it may be some kind of real-world process that you don't know. It's difficult to access, so you don't know these parameters. H is here the process, and theta are the parameters of the process. And if you don't know this, it's difficult to kind of analyze how this model is going to behave. So what we can do is that we can feed in certain input values, like put there 1 amp, 2 amps, 3 amps, 4 amps, 5 amps, and see what those output values are. And then what we have seen is that, okay, with this current you get some voltage, this current you get some voltage, and so on. So you have these discrete points. So now we have data about the process, and that helps to start modeling the process. Yeah, I have created some script to kind of simulate this kind of process and getting these values. And it looks like that these values are rather linearly distributed. They are kind of continuous, because there are so many input and output values levels, so it's probably a continuous process, and it's quite linear. So therefore, what is a model that is well suited for this kind of case is a linear regression. It's a regression because output values are continuous, and it's linear because these are linearly dependent. It could be also, if you had some other kind of process, that your values could have been like this, and then it wouldn't be so linear, and then you should try something else, like non-linear regression. But in this case, the linear regression could fit. But even whatever it is, the process of learning it and predicting is pretty much the same. So let's try to put there a linear regression. And here, this what I said earlier, that we again use numeric Python, import numeric Python library, and give it a sorter name NP. NP is now the numeric Python library. And then from the sklearn, this we do a lot in this course. sklearn is that we take something from this scikit-learn library, which is a very good library of many kinds of machine learning algorithms. And now we take a linear models category and import there one certain machine learning model called linear regression. We could have taken some other model if this wouldn't be linear, but now we believe it is. And then in this sklearn, the interface with all of these modules that we will use is pretty much the same, and they use the terminology that you have kind of x is the values that you are the input, and y is the values of output. So I have also now here put so that I have copied these input values to x and output values to y. And also this requires that the x values are a column vector. So originally here x was kind of a row vector, a vector of lot of values like this. And now with this kind of reshaping, which is a little bit ugly but simple thing to do, it now becomes a column vector. And there are certain reasons why it needs to be a column vector. It's not very nice, but we have to just do it. Convert it to column vector, and now it is the input and this is the output. And then we use this model. And now I notice that this my code is a little bit like ugly here. So maybe I change it a little bit. So I'm here first creating the model. Let's call it model unfitted. And I just take this linear regression model from this library. I don't need this here. Like this. And or let's call it like LR model, like linear regression model. So I create an instance of this linear regression, that what I have taken from this linear model library, and I can put some parameters, and now I say that fit intercept as well as true, or maybe I can actually put it false, and then I say that model equals to LR model dot fit. So what is now happening here, that I just create first a linear regression model, and then in the next line I feed it to the data. So here is what the actual learning happens. I teach the model with the data. So x is now the input data, y is the output data, and this kind of learns the coefficients so that it fits to this data as good as possible. And let's run it. Now it's done. So and then I plot it to diagnose that if it works properly. And first I have plotted here a scatter plot of those my measurements, which were I and V, and it creates these blue dots here like previously. And then I also created here a secondary x-axis or x values, more x values, which are reaching from 0 to 5. From 0 to 5, and this lin space equally spaces values between 0 to 5, certain number, maybe 500 values or something. And I also make that as a column vector with reshaping it. And then the y is the predicted values with these new x values. So now I use this model for predicting what the output would be for these new values that I have created. And now I can also plot here a line plot which has all these values, my new values from x, which are reaching from 0 to 5, and maybe 500 different values here. So I kind of make 500 new measurements and predict these values of y and plot the line there. And it's this red line, because I have said there the color is red, it will be plotted in red. And then I put some x label, input amps, and the variable output volts so that the people can understand what this diagram is, and also give some name with title unknown forward. So now I have a model and I have predicted these values, and now I can compare how these predicted values fit with the actual measurements, and it looks pretty good to me. There are some discrepancies, so that these values are not exactly in this line, but as we know, all the measurements has also noise, so it can be that it's just a normal noise which keeps them not being exactly this line. So maybe my model is really good, but the noise in the measurement is disturbing. But it can also be that there are some other things which are affecting to these output values which are not included in this model. For example, the temperature of this system. Okay, so now we have been able to somewhat predict these values for certain outputs, and also this lets us to understand this model a little bit better, because now it looks like that if we go to 0 amps, the voltage is also probably 0. If we go to 1 amps, the output is 5 volts, 2 amps, 10 volts. So it could actually be that this process is something like, because this the slope of this line is delta y per delta x, and if I take, for example, here, go from here to here, delta x is 5 volts, 5 amps. Oh, now I'm putting it in the wrong place. Yeah, so delta y is now 25 volts, and it's here, and delta x is 5 amps, so it's here. So actually there are 25 volts per 5 amps, and those who know electrical engineering knows that, okay, this looks like this system could be a process could be a resistor which value is 5 ohms. So it could be like this, that you have here a current source, then you have here one resistor, and here a voltage meter, and this resistor would be 5 ohms, and this would be the process. So now I have learned plenty of things about this process, and that helps me to understand it much better. And if we now take a look at these values, this indeed seems that this the model that I learned, its coefficients, that is the slope of the curve, is almost like 5, it's 0.96, and the interpret is 0 because I said that do not model it, and if I say that do not model it, it actually means that I assume that this the intercept is 0. What's happening? Okay, no, let's not worry about this too much. And now actually with these parameters I would say that my process would look like this, that the voltage of the output is 4.9, or actually it's 5.0 times I. So then I would have this kind of process. This should be now about 5 volts here. So I have this process now, so that the parameters of the process is about 5, and it could be indeed replaced by this kind of equivalent circuit. So now I can use this model to understand, for example, why this output exceeded, for example, some permitted limits, 20 amps perhaps, and yeah, what happened in the process and why, and also I can predict the future values and find how to make certain actions to use the process in a correct way. So all these things can be now learned when I know the process. And of course this formula is really simple, and this can be also implemented in a standard programming way. But if you instead had this kind of process where you have something like 100 input values, then it is not feasible anymore, because even if those input values would be discrete or binary, then you would have, they would be only 0 and 1, so only 2 options for each. But because you have n of them, and if n is for example 100, then you would already have 2 to the power of 100 of different input options. And how to make a program in a program to how many if clauses, or how would you implement a program that handles all this? It's doable, but it's a hard work. So therefore it's easier to with increasing complexity, it's increasing important to use machine learning instead of programming. So then I just want to only remind that whenever you are doing these machine learning models, think about what process you are modeling. What is the real world process that you are modeling? What are the inputs and outputs and parameters? Can you include those in the model? Do you know them? Can you include them? And more of these you can take into your data, the better is the model. So data is very important for these machine learning cases. And also then think about the process, if it is continuous or discrete or categorical. So if it is continuous, it's regression; it's discrete, it's classification, what you are looking for. For example, this electrical system case, it could be so that the output is only that the LED is on or off. And then you would need to know that in which input combinations the LED is on, and in which combinations it's off. But when it is continuous value, then you need a regression. And then also think about a while that if the process is stationary or changing over time. If it is changing over time, then it is non-stationary, and that means that the model that you have learned may not be valid after a while. And how to overcome that? Is it that you need to retrain your model often, or can you somehow also learn how it is changing over the time? And one also very common modeling target is to model stock markets. So this is actually a good thought exercise, that what if you are modeling at stock markets? So what is the stock value at the, for example, on the next day? That would be valuable to know. So what would be the inputs for your model if you want to model tomorrow's stock markets or electricity price or whatever strange value? So what are your inputs? Is it the previous stock market? Is it something related to this some process parameters, for example, the firm's operations, their decisions, what they are making, or what it is? And if it is an input only, what you can, or previous value only, what you can actually model then? And is this process stationary? So think about it. We can discuss it then in the lecture. Yes, that's it. I have this is what I was I thought it is necessary to say also about this modeling some warnings and something to think when doing modeling, not just blindly applying some models, but also thinking a little bit what you are actually modeling. Thank you.